Welcome everybody to this joint EPFL Center for Intelligence Systems and RIKEN Artificial Intelligence Project joint talk series on machine learning and artificial intelligence. Today we have the great pleasure to have Professor Taiji Suzuki with us, who's a star, in my personal opinion, in learning theory and in machine learning. He has done quite a bit of fundamental work in learning theory, and lately he's been focusing on deep networks and providing theoretical insights into their developments. And I'm really looking forward to your talk, Taiji, today. So take it away, please.
Thank you very much, Volkan, for your kind introduction. So yeah, it's my great pleasure to give my presentation here. So yeah, ideally it was better to have a meeting physically, but it is also good to have a meeting in this online setting. Yeah. So I would like to share my slide. So you can find the link to the slide in the chat. Okay, so please look at the slide from the link. Okay. And so today I want to talk about the optimization theories of neural networks with its statistical perspective. So yeah, this is the members of my team. So I am a team leader of the deep learning theory team. So, and there are some other members, so Sho Sonoda and Asushi Nitanda and Kenta Ono. And we also have many good collaborators. And the works I present in the following slides will include some works with those collaborators. Okay. So this is an overview of my presentation. So today I will mainly focus on the optimization theory of deep learning. So instead of a very practical optimization technique of deep learning, so I will mainly focus on some fundamental theories of optimization theory. So I will show some convergence rate or some global optimality of optimization techniques. In particular, so I will talk 4 topics. The first topic is stochastic gradient descent in neural tangential kernel regime. The next one is infinite dimensional gradient arrangement dynamics. The third one is particle gradient descent in the mean field regime. And the last one, so if I have time, so last one is about optimization theory in the double descent phenomena. And through the optimization theories, I will also mention its connection to generalization performances. So in deep learning theories, it is very difficult to decouple the optimization and the generalization. So yeah, so I should talk some connection to the generalization. So I hope you will find some connection between these 2 topics in my presentation. Okay, so basically in this presentation, so we consider a kind of an over-parameterized neural network. So that means, so we consider a very wide neural network. And it is known that if you consider a very wide neural network, so then there is no spurious local minima. Okay, so this is because the very wide neural network has a very high explicit power. So then during the optimization procedures, it can find a good decreasing directions. Then eventually it can achieve the global optimal. So that means it can achieve to the 0 training error point. Okay, to analyze such an intuition, so there are basically, roughly speaking, there are 2 types of analysis. And so the difference of a neural tangent kernel and the mean field regime is coming from the scaling of the initialization of parameters. Okay, and so to explain that, let us consider a very simple 2-layer neural network, and where AJ is a second layer's parameter and the WJ is a first layer's parameter, and the eta is a nonlinear activation functions. Okay. So if you set AJ as 1/√m, where m is the width of a neural network, then it is called a neural tangent kernel. And if you set AJ as 1/n, the scaling, so then it is called a mean field regime. So here we consider a very wide neural network, the very over-parameterized regime. So m is very large. So this difference is significant. Okay. So in the neural tangent kernels, this initialization, this scaling is much larger than the mean field regime. So there is a square to m times difference. So this difference affects the behavior of optimization. And the required analysis or required statistical tools are also very different in these two regimes. Okay. So first, we consider the neural tangent kernel regime. So this is a bit easier part. Yeah. So, so here we consider the two-layer network. So as I said, AJ is relatively large compared with the mean field regime. So the slight difference of the first layer's parameter affects the output very much. So it has a very strong impact of the slight dependence of the first layers to the output. So therefore, the neural network can be approximated by this first-order Taylor expansion. Okay, so this is just a first-order Taylor expansion, where W0 is the initialization. So the initialized parameter is W0. So around the initial solution, so we can expand like this. So this approximates the neural network very well in the neural tangent kernel regime. So therefore, so we can analyze a neural network through this approximation. So you can see that this is just a kernel model where the feature map is given by like this. Actually, so we can construct a kernel function by inner product of the feature max from over the x and x prime. So this is a symmetric and a positive function. So this can be seen as a kernel function. So this is called a neural tangent kernel. Yeah, so more precisely, the neural tangent kernel is defined in the limit of m to infinity, but this is almost a neural tangent kernel. So through this viewpoint, so we can analyze the behavior or the optimization of a neural network. So because all of them can be reduced to that of the kernel models. So there are many theories about the kernel methods. So we can import all such theories into the neural networks. Okay, so actually there are many theories about the optimization or generalization in the neural tangent kernel regimes. So this is just one of them. So this analysis is coming from this paper. So in this paper, we have analyzed a stochastic Granite descent in the neural tangent kernel regime. And so we can show that SGD can achieve the so-called minimax optimal rate. So yeah, so the minimax optimal rate is the rate which cannot be improved by any other methods. So if the true function f star is included in the RKHS corresponding to the neural tangent kernel, so then we obtain this convergence rate. So here we are considering the online settings. That means each iterations we observe one data point. So after T updates, so we obtain FT by stochastic Granite descent. Then its estimation error, the square of the L2 distance between the FT and the true function can be bounded by like this. Okay. So the first term is an error, so which decreases to 0 as the width m go to infinity. So yeah, this can be negligible in a very overparameterized settings. So the main term is the second term. So this is called minimax optimal rate. And so as I said, this is an online settings. After T iterations, we have observed m data points. So T can be interpreted as the number of training data. Okay, so you see that this is faster than 1 over squared T. So 1 over squared T, in other words, 1 over squared N. So the N is the data points, so number of data points. So this is faster than 1 over squared N, so which is a typical convergence rate or typical bound for Rademehoff complexities, but we have a faster rate than 1 over squared N. So then this is called a fast learning rate. And moreover, the convergence rate is characterized by two quantities, R and beta. And the important part is beta. So beta represents the decaying rate of the spectrum of the neural tangent kernel. The neural tangent kernel can be decomposed into orthogonal bases, and there is a corresponding spectrum, and the convergence rate is controlled by the spectrum. So in that sense, here appears an inductive bias. The structure of the neural tangent kernel controls the learning abilities. Okay. So there's another parameter R. So R represents the location of the true function. If the true function is included in very small subspace of the RKHS corresponding to the neural tangent kernel, so then R can be large. And if the true function is very far away from the RKHS, so then R can be very small. Then the rate could be slower. But anyway, so we have this rate. And if you look at the proof, so we see this kind of behavioral stochastic descent. So during the optimization, at the first part, it finds the low frequency component that corresponds to the principal component of the neural tangent kernel. Then after that, it gradually captures high frequency component. So if you stop at the appropriate point, so then you can avoid the overfitting. Then you get the fast learning rate like this. Yeah. So this is nice. So yeah, this convergence rate captures the inductive bias of the feature map constructed by induced by the neural networks. But analysis of a kernel method is not satisfactory in some sense. So to see that, let us consider a very simple non-parametric regression problem. This is just non-parametric regression problem, and we assume that the true function is in a class of a very simple piecewise constant function with 3 jumps like this. So maybe 3 can be 4 or 2, so anything is okay. But anyway, so here we consider a 3-jump piecewise constant function. We know that there is a 3 jumps, but we don't know the location. Okay, so this is very simple, but to estimate this kind of functions, the worst case error of the kernel rich regression can be lower bounded by like this, 1 over square root n. So for any kernel functions, there is a very worst case true function such that the learning rate is lower bounded by 1 over square root n. So here we are examining the mean square error. Okay, so but on the other hand, if you apply the deep learning, so you obtain 1 over n convergence rate. So there is a square to n difference. So this difference is significant. So this difference is coming from the feature extraction ability of deep learning. So in a kernel method, it cannot find a good feature. So then it cannot find the location of the jump. So then it suffers from the suboptimal rate. But the deep learning can find intuitively, so deep learning can find the location of the jumps in the internal layer. So then it achieves 1 over n convergence rate. So yeah, to analyze such a feature extraction ability of a deep learning, so we need to go beyond the neural tangent kernel. Of course, neural tangent kernel, we can run many things from neural tangent kernel regime. So, so as for the feature extraction ability, so we need to consider non-NTK regime. But the problem is that if we are out of the neural tangent kernel regime, so then the model is no longer linear. So then the objective function is non-convex. So we need to deal with a non-convex objective function. But in practice, SGD works well. So why is it? So one intuitive explanation is that the SGD is a noisy gradient descent. So because it has some noisy perturbation, so it can escape from local optimal and then it can achieve the global optimal. Yeah, that is one explanation. So then we can show that in rigorous way. Actually, in the finite dimensional case, there are many works that shows that kind of phenomenon. So noisy gradient descent can eventually find the global optimal. But in our analysis, we extended that to infinite dimensional situations. So in overparametered settings, we should consider almost infinite dimensional settings because the width is very large. So to deal with such a high dimensional settings, so we consider infinite dimensional space, and then we can also show that the noisy gradient descent can find the global optimal even in an infinite dimensional situation. Okay, so now I want to explain this in more details. Well, to consider that, let us consider the loss function by a squared loss, defined by squared loss. And here FW is the model parameterized by W. And maybe FW can be 2-layer neural network, or maybe FW can be ResNet. Yeah. So we can allow infinite with this neural network. Okay. So, but just minimizing this loss function would lead to overfitting. So to avoid the overfitting, we add the L2 regularization here. But here, for technical reasons, so we don't consider a simple Euclidean norm, but we consider some weighted L2 norm like this. So unacyclic weighted L2 norm is considered. So M square is coming here. So WM square should converge to 0 faster than 1 over M square. So maybe, so if you are very familiar to the kernel method, so this can be seen as one of the RKHS node. Yeah. But this is an infinite dimensional non-convex optimization problem. So this is a very difficult problem. Okay. So, but yeah, this is a difficult problem. Okay, so to optimize that, so we consider this stochastic gradient, the Granite Langevin dynamics, which is defined by this stochastic differential equation. Okay, and this is basically the gradient descent. If you stop here, so this is a gradient descent, but we add this Brownian motion term. So this is a noisy part. The strength of the noisy part is controlled by the inverse temperature parameter beta. So if beta is large, this noisy part is small. So yeah, but this is a continuous time dynamics. So we discretize this dynamics like this. This is a discrete time dynamics. Maybe you are more familiar to this formulation. So this is just an Euler-Mariama scheme of this stochastic differential equations. So you can see that this is a gradient descent. So if you stop here, so this is a gradient descent where the step size is eta. But we add a Gaussian noise like this. Gaussian noise is coming here. So in an ideal setting, so ideally, so we want to analyze SGD directly, but instead of analyzing an SGD, so we consider this noisy gradient descent by using the Gaussian noise injection. Okay, this is a Gaussian noise injection. So because this is much easier to analyze. Yeah. More precisely, so this L2 norm is not bounded, so we should replace this by the RKHS norm or WK+1. So this is called a semi-implicit Euler scheme, but this is a more like a technical detail. So you may consider this Euler-Maria scheme. Okay, so a good point of a Granite Langevin dynamics is that it has an invariant measure pi infinity, and it is given by like this. Yeah. The invariant measure is a stationary distribution. Okay, the invariant measure of the Granite Langevin dynamics is given by exponential minus beta times the objective function. Okay, so therefore, if beta is large, so the invariant measure concentrates around the optimal solution of the objective function. And moreover, so the important point here is that this is a kind of a base posterior distribution. Okay, so this is a likelihood function, and this is a prior distribution. So more precisely, this is a Gaussian distribution, and so because this is an infinite dimensional situation, so this is a Gaussian process prior is coming here. So therefore, the invariant measure becomes something like a base posterior distribution with Gaussian process prior distribution. Yeah. So then through this viewpoint, we can analyze the generalization error and expected loss of the solution obtained by gradient Langevin dynamics. Okay, so to do so, we needed to show that the solution converges to the invariant measure. Okay, so that convergence rate can be given by like this. Here, pi infinity is the stationary distribution, and pi k is the marginal distribution of the solution WK, the case step solution. Okay, and we can show that it's weak convergence. So that the weak convergence of pi k to pi infinity can be shown like this. The convergence rate can be upper bounded by like this. The first term is exponential to the k eta. So if the number of steps k is increasing, the number of iterations k goes to infinity. So then the first term converges to 0 in exponential order. And the second term is coming from the timing discretization. So it is completely characterized by step size. So this is about the square root of eta. So kappa is an arbitrary small positive error. So this is like a square root of eta. So if you use a very small step size, so then the second term is also almost negligible. So then from this, we can show the convergence to the stationary distribution. Yeah. So this is nice, but I should mention that these constant, here is some constant of lambda infinity. So this is called the spectral gap. The spectral gap has a heavy dependency on the inverse temperature beta. So actually, lambda star has a exponential dependency on the inverse temperature beta. So yeah, so if beta is very large, so we need exponential number of iterations. So there is no free lunch. But if the loss landscape is very good, like a convex function, so then this spectral gap can be very, very small. Spectral gap is not so much small. Yeah, so, but anyway, so we can show the convergence like this. So then by using this formulation, so we can bound the generalization error like this. So now, so we bounce the generalization gap. So this is an expected loss of the case step solution. This is a training loss of that solution. That gap can be bounded by like this. So and this is basically 1 over square root n rate. And plus, this is an optimization error. Optimization error is coming here. So after the sufficient number of iterations, so this optimization error is very small. So then this term is dominant. So in that setting, so we have 1 over squared and convergence rate. Yeah, so this is a typical rate. So next, let us consider excess risk. Excess risk bounds the expected loss of the estimated W hat and the minimum expected loss. Okay, so instead of bounding the gap between the training error and the expected error, so we bound the gap between the expected error of the solution W hat and the optimal error, optimal expected loss. Okay, so in this analysis here, we assume some conditions like this. So the most important or most strongest assumption is that the true function is included in our model. Yeah, so we assume this kind of a very strong assumption. And moreover, we assume some model complexity like this, but this is very complicated, so I don't go much in details. And with other conditions, so we have this general convergence rate. So yeah, this expression is very overwhelming. So I don't go much into details, but I will explain more details in simple settings. Okay. But anyway, so the important part is coming here. So please neglect the other part. The excess risk at the case step solution is bounded by so this quantity, and the important point is here. You see that n2 minus 1 over something is coming here. So this is faster than 1 over square root n. So then this is called the fast running rate. And moreover, the running rate is characterized by 3 parameters, s and alpha, tilde, and theta. And s is basically 1. Yeah, so you can neglect s. So for example, if you use a squared loss, s can be 1. And if you use a logistic loss, s can be 1. So you can neglect that one. And another parameter, alpha, tilde, and theta. So alpha, tilde, roughly speaking, alpha, tilde characterizes the complexity of the model. So yeah, so the complexity of the model is formally characterized by the covering number of the model. So such information is coming here. And the theta represents the location of the true function. So if the true function is very a kind of out of the model, so it is included in the model, but it is very, very far away from the origin. So then theta is large. But if the true function is included in some subspace, very small subspace of the true our model, so then theta can be high. So yeah, anyway, it's the complexity of the model and the location of the true function characterizes the convergence rate of the excess risk. But this is very, very complicated. So I want to go to more easy examples. Okay. So let us consider a very simple two-layer two-layer neural network that is given by like this. Okay, so an AM and a BM are some fixed parameters. So that is a kind of scaling parameters. And so we train W1M and W2M. And we assume that the true function is included in this very simple, teacher model. And the true function is included in this model. And moreover, so we fit this model to that data. So here, W star is the parameter of the two functions. So then we assume that it satisfies these conditions. Okay. And so W star 1M and W star 2M is the parameters of the mth neuron of the true function. So this one is coming here. And we assume that the magnitude of the square of the mth neurons parameter should converge faster than M2 minus 2 gamma. Okay. So we assume this summation is bounded. So that means that the magnitude of the parameters of mth neuron should go to 0 faster than m2 minus gamma. So that means the gamma controls the rate of the components. So gamma controls a kind of complexity of the model, complexity of the true function. So if gamma is large, so then it decays very rapidly, and if gamma is small, so it doesn't decay so rapidly. Okay, so then from this observation model, so we fit this model to the data by using the gradient arrangement dynamics. So then the solution F hat obtained by the gradient arrangement dynamics satisfies this rate of convergence in terms of the this mean square error. This is the square of the L2 distance between the estimator and the true function. Okay, so this is some general results. So I show these simplified versions. So you see that if you use if you fit this neural network model to the data by using gradient management dynamics, then you get this kind of fast learning rate. So actually, if gamma is large, so the complexity of the true function is very low. So it is a kind of a simple function. So then it approaches to 1/n convergence rate. So this is fast. But if you use the kernel method, so then the worst case error is lower bounded by this convergence rate. So you see that in the rate of convergence, there appears the dimensionality D. So it suffers from the curse of dimensionality. Then if D is large, so if you consider very high dimensional settings, then this rate of convergence becomes like 1/square root n. So we again see the square root n times difference. Okay, so this is because the deep learning has some feature extraction ability. So during the optimization, it can find a good direction of features, and then it achieves a fast learning rate. But if you use the kernel method, so it cannot find a good direction. So then eventually it suffers from the curse of dimensionality. So yeah, this result shows the separation of estimation performance with optimization guarantee. Okay, so then next we are going to another optimization method for in mean field settings. Okay. Well, so in the previous slide, so we have considered a kind of a mean field regime, but we have assumed that the magnitude of parameters decays as the index of the neurons go to increase. So, but here we consider that a situation where the magnitude of each neuron is almost the same. Okay, so that is more like a pure mean field settings. Okay, so in the mean field settings, the parameters initialize like 1/m order. So then it can be written by like this. Here, the Rj and the Wj have the same order, like order 1 across the different neurons. So then the two-layer neural network in the mean field regime can be seen as the average of the outputs from all neurons. Okay. So, but the problem is that this is nonlinear with respect to the parameters of Rnj and Wj. So the optimization is basically difficult. But here we take the limit of infinite widths. So we take the m to infinity. So then this finite sum can be converged to something like this integral representations, where nu is the distribution, some distribution on the parameters R and W, and the first and the second layers parameters. So, sorry, so this eta should be sigma, but anyway, so we have this integral representations. Okay, so actually the finite width neural network is one special case of this integral representation. So because if you set this measure as a sum of the Dirac measure, so then this representation can be reduced to this finite sum. So this is a kind of extension. Okay, so a good point of this integral representation is that this is linear with respect to the probability measure nu. Okay, so if you consider the parameters, this is not linear. So this is a very much non-linear, non-convex objective. But if you look at the probability measure on the parameters R and W, so this is linear. So this is just a linear model. So then we can analyze some convergence rate. Okay, so now, so we propose some new method to optimize this mean field settings. Okay. And so by using the integral representation, so then optimization problem of a two-layer neural network in a mean field regime can be reformulated like this. Okay, so here is the expectation of H theta with respect to the distribution nu, where H theta is the one neuron. Okay, theta is the couple of R and W, and H theta X is given by this one. So this is one neuron. And by taking its average with respect to the, some probability measure nu, so then we get some two-layer neuron, two-layer neural network like this. Okay, so please remember that. So this is an expectation of each neuron with respect to the distribution nu. So that integral representation is the same as this expectation, where H theta is each neuron. Okay, so just minimizing this loss function leads to overfitting. So we add L2 regularization. Here again appears some expectation by the property measure nu. But the space of the property measure is too large, so then it is a bit difficult to optimize or realize this optimization directly. So we restrict the set of the feasible solution to absolutely continuous probability measures like this. To do so, we add an additional negative entropy regularization. So then the feasible solution is restricted to the measures with density functions. Okay, so by using the density function, so this can be rewritten by like this, and this can be rewritten by like this, and so the objective function becomes like this. If you look at these two terms, you can see that this is just a KL divergence from Gaussian distribution. But anyway, so our objective is to optimize this objective function. Okay, so you see that this is a convex with respect to the density function Q. So yeah, so maybe, so it is easy. So actually, so we can apply a standard convex optimization technique to optimize this objective function. But the problem is that the density function Q is a kind of an infinite dimensional objective. So yeah, this is basically infinite dimensional optimization problem. And actually there appears an integral like this. So yeah, we don't have any closed form representation of this integral. So we need to do some approximation about this integral. For that purpose, we approximate this integral by some particle. Using a particle, so we sample some particle from the density function Q, and then instead of this integral, we consider a finite sum over the particles. So then, so we can approximate this integral. Okay, so here is some overview of our method, our proposed method. And so as I said, we want to optimize this objective function, but the difficulty is that this is not linear. Because the loss function L is a nonlinear function. So this is a nonlinear objective function. So then we try to linearize this objective. So basically, so we take its gradient with respect to the density function Q, then we linearize this like this. So this is a linear function with respect to the density function Q. And so G bar T, so to determine G bar T, so we use the so-called dual averaging techniques. So this is a very famous technique that was proposed by Nesterov, and so this has been well investigated in a finite dimensional optimization from literatures. Okay, so the determination of G bar T is written like here. So at each iteration, so basically, so each iteration we calculate the gradient for the loss function and the regularization term. It is written by GT, and we take its weighted average like this. That is a G bar T. So because we take average of the gradient, so it is called the dual average. Okay. So anyway, so we have a linearization of the loss function. Then we obtain this approximated objective function. Okay. So the next objective is to optimize this objective function. But fortunately, so there is a closed form solution of this optimization problem like this. So the optimal solution of this optimization problem is given by like this: exponentially minus G bar T divided by lambda 2. So we have the explicit form. So then we set this solution as the next update. So then, once we have a QT or QT plus 1, then we can calculate the gradient at the next update. So then we can update the G bar. So then we repeat the same thing in the next update. So then we can iterate we can update QT in such a manner. Okay, so that is an outline of our method. But the problem is that to calculate the gradient, we require to calculate the output from the neural network. So that is given by the expectation with respect to the distribution QT. So here appears the expectations. So this is approximated by some MCMC method. So you can apply any MCMC method that is sampled that samples particles from this distribution. So for example, you may use the Granite Rangeman dynamics. As I said, so as I have shown in the previous slide, so this gradient Rangeman dynamics has stationary distribution QT plus 1. So the stationary distribution of this Granite Rangeman dynamics coincides with this solution. So yeah, you can use the Granite Rangeman dynamics to sample some particles from this distribution. So then suppose that we have a sample the M particles from the distribution. So then the expectation can be approximated by this finite average. Yeah. So this is the overview of our method. So this is a more detailed description of our proposed method. Okay, so we calculate the gradient, we calculate the dual averaging, and then from this one, so we can determine the next update. Then from this next update, so we sample the particles by using some MCMC method like Granite Rangeman dynamics. Then we iterate this one. Yeah. So if we consider this optimization method, so then we have this convergence rate. Yeah. As for the outer loop, we have 1/t convergence rate. So this is coming from the analysis of a standard convergence rate analysis of a dual averaging method. Yeah. So yeah, we have a 1/t convergence rate. So this is optimal in online settings. Yeah. So our method can be applied to the online settings, so where we observe one data point per iterations. And as for the inner loop, to obtain a good approximation of the integral, so it requires this iteration, this number of iterations for the gradient Rangeman dynamics. It is basically t square at the t step iteration. So we need to run gradient Rangeman dynamics t square iterations. So there are some constant depending on the regularization. But if you neglect here, it is basically t square. So then the total complexity to obtain epsilon optimal solution is like a epsilon to minus third. Yeah. So this is a polynomial order convergence rate. So as for the number of particles to require to obtain the epsilon optimal solution, so that is so we can set epsilon to minus twice, epsilon minus 2 times the polynomial order of n and d. So here, so in terms of the number of particles, it is also still the polynomial orders. Then the total computational complexity is also the polynomial order. Okay, but I should say that so there is an exponential dependency on the regularization parameter lambda 2. So this is a regularization parameter for negative entropy. So if lambda 2 is very small, so then this term becomes large. Well, this is a kind of annoying term, but I think so. We conjecture that so this is unavoidable. Yeah, yeah. So without any additional assumptions, I think this exponential dependency is unavoidable. Okay, so yeah, this is good. So because we have a 1/t convergence rate, but maybe if you are very familiar to stochastic gradient descent or stochastic optimizations, so we can improve the convergence rate to an exponential order if we consider finite sample empirical risk minimization problem. So the dual averaging method can be applied to online settings. But if we optimize empirical risk, so suppose that we have a finite data points, and so we can define the empirical risk corresponding to the data points. So if the sample size is fixed, so then we can improve the convergence rate like this. So to do so, we apply the stochastic dual coordinate ascent. Then we get this convergence rate instead of 1/t. So to achieve epsilon accuracy, so if you use the SDCA, so the number of outer iteration becomes like this: n plus L divided by mu times log 1 over epsilon. So n is the sample size of the data points, and L is the smoothness of loss function, and the mu is the strong convexity. And here is a log order dependency to the target accuracy epsilon. So we have an exponential convergence in terms of the outer iteration. But some difficulty is that it is not so trivial to combine the SDCA and such a particle method. And moreover, we want to skip the number of resampling as many as possible. So these are the two problems. Okay. So this is a so to do so, to combine the SDCA method, so we consider a dual objective function. Okay, so this is a primary objective function that we have considered in the previous slide. Okay, so we want to optimize this one. So to optimize this one, we consider its dual like this. By a Fenchel duality theorem, the dual objective function is given by like this. Here, Li star is a Legendre transform of the loss function Li. Yeah. And moreover, so the dual variable is an n-dimensional vector like this. So the dual variable is written by G, so which is a n-dimensional vector. So in the primal, it is the primal variable is an infinite dimensional objective. So P is like an infinite dimensional one. But in the dual, the variable is an n-dimensional vector. So this is one of a good point about the dual objective function. Okay, and moreover, if you look at the dual loss functions, this is separated to each coordinate. Okay, so this is just a sum of the convex functions with respect to each coordinate. So this is very easy to optimize. Okay, so just to optimize these loss functions, you needed to just optimize each coordinate independently. So it is very easy. But there is a second term, so there is a correlation between GI. Okay. The second term is written by like this. Here, QG is defined by like this. So this is very similar to the PT, QT we have considered in the previous slide. But anyway, so QG is defined by like this. And accordingly, we define the PG like this. This is a normalized density function. So this is a primary variable corresponding to the dual variable G. Okay. So our strategy is like this. We randomly pick up one coordinate I at each iteration and then optimize that coordinate. Okay, so each coordinate corresponds to one data point. The i's coordinate corresponds to i's observations. So this means that at each iteration, we pick up one data point from n observations. So we have a n training data. So we pick up one data point from that, and then we update the coordinate corresponding to that data point. Okay, so that is our main strategy. So this is our concrete update rule. So we pick up one coordinate like I. So we update GI. So then this objective function can be upper bounded by this quantity. So here is some nonlinear term. So this can be approximated. This can be upper bounded by this quadratic function with respect to the coordinate GI. So yeah, so we can show this upper bound. So then we optimize this objective function with respect to the i's coordinate GI. So this is a one-dimensional optimization problem, so it is easy to obtain the optimal solution. Then other coordinates are fixed. Now, according to this update, so we update a primary variable like this. So P of G bar T plus 1 is defined by this one. So G is coming here. So depending on the G, so P is defined. Okay. Yeah, so but the problem is that, so here is an expectation with respect to the T's update of the primary variable, PT. So we needed some approximation with this integral. Yes, so you may apply any MEC method, but anyway, so suppose that we have particles, we have sampled some particles from these distributions, the T-step solutions. So then we can approximate this integral by a finite sum using this particle like this. Okay, so suppose that at 0 iterations we have we have sampled some particles from the solutions. So then we set the weight of the particle as 1/m. Okay, so once we have sampled, so then we refresh the particle after n tilde iterations. So before we refresh the particles, we update the weight of each particle like this. So this is like an importance weighting. So yeah, the update of each particle, update of the weight of each particle is coming from the density ratio of the first solution, so first step solution and the t-step solutions. So that update rule is given by like this. But yeah. But anyway, so we can update the weight. Okay, so this is the overview of our method. So here is a more detailed descriptions. At each iteration, so we sample some particles. At every n tilde iterations, we obtain the particles from the primal distribution. And then by using that particle, so we optimize the dual variable like this. So where IT is a randomly chosen coordinate. And accordingly, we update the weight of the particle like this. So we iterate like this. Yeah. So then here is a convergence rate analysis of our proposal. Yeah. So suppose some assumptions. For example, loss function is 1/gamma smooth, and some additional technical conditions. We have this convergence rate. So yeah, the number of resampling interval n tilde is assumed to satisfy this condition. So n tilde divided by n lambda 2 is order 1. So under some assumptions, if you take the number of particle m star is like 1/epsilon lambda, where epsilon is a target accuracy, and lambda 2 is a regularization parameter of the negative entropy. So then, after this number of iterations, you get the duality gap bound like epsilon. Yeah, and as for the number of outer iterations, it is like a log of 1/epsilon. So the dependency on the epsilon is just a log. So this means that exponential order of convergence in terms of the outer iteration. And here is n plus 1/lambda to gamma. And if you use the deterministic optimization method, so instead of stochastic coordinate, if you update all coordinates at each iterations, the complexity of the Granite computation becomes n divided by lambda to gamma. So where this one is a condition number. So there is something like a multiplication of n and a condition number. So but if you use a stochastic optimization, stochastic coordinate descent, so this n and the condition number is decoupled, like n plus the condition number. Yeah, so this is a good point of stochastic method. And then the total complexity can be written by like this. So this is a polynomial with respect to the sample size and the target accuracy epsilon. But here we again note that the K star is a complexity of the sampling. So here again some exponential dependency with respect to the regulation parameter lambda 2. But we think it is an unavoidable dependency. Yeah. Okay. Okay. So the final topic is the double descent and optimization. So because I don't have so much time, so I go through this topic quickly. So actually, yeah. So this part is coming from this paper, and this work is mainly initiated by Denny Yu. He is one of the collaborator with us. Yeah. So in a standard machine learning books, we see bias and variance trade-off. If you increase the complexity of the model, so then the bias will decrease and the variance will increase. So then the sum of the bias and the variance is the predictive risk. So you needed to find you need to balance the bias and the variance to obtain the minimum predictive risk. So that is a common sense. But if you increase the complexity of model beyond the sample size, so then we see another decrease of the predictive risk. So this is called the double descent. And if the predictive risk around here is better than this one, so this is called benign overfitting. So even if the the model is overfitted. So it can predict the next outcome very well. Yeah, so the situation of the benign overfitting can be depicted like this. But anyway, so there is so this is one of the hot topics in deep learning theories. Okay, so because we are considering the overparametered setting, so then it is included in this double descent regime. So to analyze that, so we consider overparametered settings where the dimensionality D is much larger than the sample size. And moreover here, so instead of neural networks, we consider a very simple linear model. Okay, so here, so the beta star is a true signal. So we want to estimate this from the n data points. To estimate the beta star, so we consider this interpolation. So minimum interpolator given by like this. Okay, so here beta, we assume that the beta satisfies this condition. So that means we completely overfit the model to the data. Okay, this is a training here, the training error is 0. So this is very much overfitted. So here is some observation noise. So in classic text, so this is not a good estimator, but yeah. So here we consider overfitting here. But it's among the feasible set that satisfies these conditions, we pick up the minimum normal solution. So that can be seen as the simplest solution among the feasible solutions. Okay. So in usual settings, so we consider Euclidean norm as a norm, but we consider more general settings where P is coming here. So P is a positive symmetric positive definite symmetric matrix is coming here. So we consider a more general matrix. So this solution corresponds to the solution obtained by this preconditional Granite descent. So suppose that we start from the origin, then we optimize the parameter by using this preconditional Granite descent. So then the obtained solution becomes like this. So if P is P is identity, so this is a Granite descent. And if P is an inverse of the variance and the covariance matrix, so then it is called a natural Granite descent. So here we consider some population version of a variance and covariance matrix. Okay. So the question is, so how to choose the preconditional P? So what is the optimal P? So this is the overview of our result. So the predictive risk, the mean squared error, the predictive risk can be decomposed into this bias and the variance term by taking a proportion limit where the dimensionality D and the sample size go to infinity and the ratio of D and N goes to some positive real gamma, which is larger than 1. So then we have an exact evaluation of bias and variance in the asymptotics. So through that exact evaluation, so we can show that the variance can be minimized by natural Granite descent over all preconditional P. So yeah. And as for the bias, so there is no free lunch. So we cannot obtain the optimal P a priori. So the optimal P depends on the true parameter beta star. So roughly speaking, if the beta star and the beta star is along with the principal component of input X, so then the gradient descent is better than natural gradient descent. But if beta star is not along with the principal component, so in that such a misaligned case, the principal component of X and beta star is misaligned. So in that case, the natural gradient descent is better. So combining these two notions, so maybe so the best method would be the combination or interpolation of the gradient descent and natural gradient descent. So this is better than the gradient descent and natural gradient descent. And actually from the numerical experiment, we have confirmed that. Okay, so but I skipped some details. Okay, so this is a summary. So thank you for listening. So I want to take some questions.
Thank you very much, Taiji, for this fantastic talk. Just if I may quickly add, so in the Langevin work, you think about learning distributions over the weights of the neural network. Mm-hmm. You notice that learning problem is in fact a sampling problem with an appropriate, let's say, I mean, there's some sort of a connection with some temperature parameter, mm-hmm. and you apply Langevin dynamics to get maybe samples out of these distributions with particles. Is this the general strategy?
Yeah. I see. So you mean this one? Maybe
Yes.
around here. Okay. So you mean so the strategy is that we sample around the particle from this distribution by Langevin dynamics. So that is a
Is that the strategy? Yeah.
Yes. That's right. Yeah.
Okay.
So here there is no temperature parameter beta. So because
sorry, I there was a temperature parameter Langevin before, so I confused that one. Yes.
Yeah. Okay. So here, well, so in this case, so so here, so there appears a temperature parameter beta. Yeah. So here, so we are estimating the infinite dimensional parameters, but in the later part, we estimate a distribution. So this is estimating an infinite dimensional parameters, but the later one is estimating the distribution. So that is a very different. So maybe we can consider intermediate case, but we don't have any good theories about that. Yeah. So there are two ways to represent the overparametered networks. So the overparametered network, we consider a distribution of parameters that represents the neural network, or maybe we can another option is that we consider we just consider the infinite many parameters, just one set of parameters. So there are two options. So,
there are two options. I think we also had some work on applying this distribution learning over the parameters for GANs. We had a paper with my PhD student Yaping C, and it actually works well in practice, also in GAN. So this is a very powerful idea. Thank you for presenting it. One last quick question from me. The work on SDCA, is this online? The work that you mentioned with the faster rate, with the coordinate descent, with the dual averaging.
I see. No.
Okay.
So in the coordinate descent, it's it's not online.
Okay.
So first part, particular dual
very
method
fascinating.
Yeah.
Very fascinating work. Yeah.
Thank you.
There are some questions in the Q&A.
Yes. Okay. So I answer by myself. The first question is that, okay, so could you show the adequate use case for SGD, momentum atom for each other? Okay, so yeah, this is a very important question, but this kind of a question is not covered by my theorem. So yeah, of course, this is practically this is very important, and other guys try to find a question to these kind of questions. But maybe in this part, so okay, so in a double descent case, so we have analyzed best choice of the preconditioner. So in some cases, energy natural gradient descent is better. So maybe Adam or the adaptive method can be seen as approximation of a natural gradient descent. So yeah, so these kind of analysis gives some answer to that questions. Okay, so the next question is, what is the current sort of optimizer for deep learning instead of Adam? Maybe, so this is not, this is also out for my my research, because this is more like I think more practical side. Yeah, as far as I know, so it also depends on the model. So we cannot say what is the best one. So whether, yeah, for example, to optimize the transformer, maybe Adam is good, but to optimize VZZ 13 or something like that, maybe the momentum SGD could be better. So yeah, there are many practical observations. So yeah, yeah, so please look at such a practical papers. Yeah. And is it possible to apply Bayesian optimization methods to optimize variable parameters for deep learning training? If it is true, so what are the benefits of use Bayesian optimization? If it is possible, the Bayesian optimization method to optimize variable parameters means there are some hyperparameters, something like that. Yes, of course. Yeah, Bayesian optimization is useful. Yeah. But but Bayesian optimization. So of course, my research is a little bit relevant to Bayesian optimization. For example, the infinite dimensional range-bound dynamics can be applied to Bayesian optimization. So it can find a global optimal. So yeah, but it is a little bit out of my research. So of course, Bayesian optimization is useful. Yeah. Are there any efficient cases concerned Bayesian deep learning method? And could you show the reference materials, URL and so on? Are there any efficient cases concerned Bayesian deep learning method? So are you considering some Bayesian method for estimating deep learnings?
So perhaps some of these talks, some of these questions are not quite related. Maybe we can answer them offline or something like this.
Okay, yeah, I'm sorry. So this is also not so much related to my presentation. So please skip. Please let me skip here. And is it possible to adapt Wasserstein distance instead of Kerr divergence? Okay, maybe I guess here. So the Kerr divergence between the okay, so the normal distribution and the current distribution, maybe. I'm not sure. So which part is your interest? But maybe you are saying about that. So maybe so we can replace the Kerr divergence by Wasserstein distance. But our method strongly relies on the Kerr divergence. So for example, the next update, so this update rule is strongly coming from the Kerr divergence. So it is not so obvious. Yeah, that is my answers. Maybe you are saying about the convergence of the range-bound dynamics in terms of the Kerr divergence. Yeah. So, but if the log homomorphic inequality is satisfied, so then the Kerr divergence can be lower bounded by the Wasserstein distance. So yeah, you can also ensure the Wasserstein distance convergence. And so, okay, so I have another 4 questions. Is it possible to theoretically find a point of the global minimum in deep learning model learning without the heuristics method, for instance, early stopping and so on? Well, the early stopping is not, I think the early stopping is not heuristics. Early stopping is one of a good important ingredients of optimization technique. So actually, for example, so this convergence rate analysis, so we terminate at the finite number of steps. So this can be seen as an early stopping. So based on the statistical learning theory, so there appears a bias and a bias variance trade-off. So early stopping is useful for as a regularization. So, and moreover, by using something like a Granite range-bound dynamics series, so you can show the global optimality of such a noisy grand descent. Yeah, and moreover, the sufficient number of iterations are also analyzed in those analyses. So, okay, so the next question is, could this optimization theory be applied to transformer attention training? This means that, so the range-bound dynamics maybe. Yeah, I think so. Yeah, I think so. So because the infinite dimensional range-bound dynamics can be applied to any infinite dimensional problem. So it can be applied to transformer or attention training. Yes. But as for the excess risk or generalization error bound, so I guess we need some additional works. Yeah. So the next question is, in your gradient range-bound dynamics in RKH's paper, you said the regularization parameter lambda is greater than C for a strictly positive constant C. If we consider it in approximation theory, lambda decays with training data. Yeah. What's the gap between this? Well, I guess, so we didn't assume that regularization parameter is strongly positive, but I think to interpret the convergence rate, we have assumed this kind of conditions. The convergence rate can be derived for arbitrary regularization parameter lambda. But as I said, lambda has some strong dependency on the spectral gap. So if lambda is very, very small, then spectral gap can be very small. So then the ratable convergence becomes very small. So yeah, to explicitly show some dependency of the spectral gap to other parameters, I guess we have assumed these assumptions. Yeah. So sorry, I forgot some details, but yeah. that should be so. In the last work, by choosing a good P to combine granite and natural granite, what is the goal of this strategy? Is it for good balance between bias and variance? Yeah, that's right. That's right. As I said, to minimize the variance, the natural granite descent is the optimal one. But to minimize the bias, the mixture is better. So to obtain a good bias and variance trade-off, the mixture of the granite descent and the natural granite descent is better. Yeah. So the final question, so where can we access to the slide? Oh, sorry, so that's, yeah, I will make it public, yeah, just after this presentation. So, yeah.
You can also post it on your Twitter. I think people can read
it. Yes, I will do that. Oh, I have another question. So is it okay to answer that? Professor, so very nice. Do you have a comment about following? Your method sample in primal space and then in dual space, you approximate the nonlinear loss to the linear one and solve it. Yeah. Is it we going again the very nature of the gradient descent? So, or also, if distribution is for convex case, how sure we are we reach optimal side? Sampling particle from density and sorry, this is very long, so maybe so I can answer afterward. So online, yeah. So sorry, offline. So maybe, yeah. So right. I will answer later on. So.
So thank you, Taiji. This was fantastic. I also learned quite a bit and gave me many ideas that I would like to also follow up. So thank you for this fantastic talk again.
Thank you very much.
All right, this concludes our session, I believe.
Okay, so
thanks everybody for coming to Professor Taiji Suzuki's talk.
So bye-bye.